Hello. So today we're gonna do two experiments, experiment number 5 and experiment number 6. So they are both related to transformers efficiency. In experiment number 5, we will actually examine transformers efficiency by using R load, resistive load. And in case of experiment 6, we're going to check transformer's efficiency for lagging load. So that means RL load, resistive and inductive load. So the basic formula uh, of efficiency for anything will be power output over power input times 100, and that will give us percentage of efficiency. And power output is nothing but power input minus power loss. And for a transformer, in our case a single phase transformer, power losses are normally copper loss and core loss. We have already learned this. So for particularly this experiment, we are going to use the first formula, which is power output over power input times 100. So let's go back to the slides again. So in this experiment, what we are going to do is we are going to supply the high voltage side, and also in some case in second step there will be 4 steps, two for each of the experiments. For instance, experiment number 5 will have 2 steps. One time we'll supply the primary side with 140 volts, and second step will apply the secondary side with 70 volts. So primary, when we supply, we'll supply the primary side with 140 volts. At that time, the loads will be connected with the secondary side. Same goes for experiment number 6. The main difference, basic difference between 5 and 6, as I've told you earlier, like in case of experiment number 5, the load for each cases will be resistive, and for inductive load it will be sorry, for experiment number 6, the loads are RL loads, just like this figure. Anyway, so what we're going to do is I will show you the experimental verification. So not verification, experiment. I will conduct the experiment, and you need to actually um, write down the major key points, like major points, um, like measurement values, not key points, measurement values for each steps. I'll explain everything. So let's talk about this procedure. We will actually connect initially for R load, we'll connect the circuit like this, and we supply 140 volts. And you know there are 6 resistive steps in our experimental setup. So we'll change each setup, and we'll measure input power and output power, and we'll calculate for each step, we'll calculate uh, the efficiency. So it's that simple for the first case, experiment number 5. Experiment number 6 is also pretty similar, but in this case, we'll have to make sure that the supply, not the supply, load end, the power factor is constant. So um, remember to adjust reactive load for each step to have constant 0.8 power factor. When I'll demonstrate the experiment, you will understand, but still I'm telling you that when we supply to the primary or secondary, it doesn't really matter. On the load side, always the power factor needs to be 0.8. We know we can actually change the value of resistance by stepping up or stepping down. There are 5 or 6 steps total. And for inductive load, we know there is a dial, we can change it to increase the amount of inductance or capacitance. So we can change the value. Um, so we will do that. And for that, after for each step of this experiment, I told you there are 2 steps for each experiment. So this will be case 1. So we'll have for case 1 we'll have one table. For case 2 we'll have another one. Like this way there are 4 cases, and also there will be 4 tables and 4 graphs. I'll expect everything after that. So what we'll measure? So initially when we supply to the primary side, to the transformer, so the supply voltage will be 140 volt. When we supply to the secondary side, in that case it will be 70 volts. So let's talk about table 1 with R load and having a supply voltage as 140. In this case, we'll change 5 resistive values of the load, this R load. So you will get like PV1, that means supply voltage power. Then PV2, the load side power, and cos theta, supply side power factor, and load side power factor. And with these 2 values, PV2 and PV1, we can calculate simply by using this equation. So after calculating the efficiency, we'll get the efficiency and we'll put it here. We'll write it here. So for 6 different resistive value, we'll get 6 different uh, value of efficiency. So this is for R load when we supply to the primary side, when we'll supply to the secondary side, and then again we'll change R values and we'll calculate the efficiency in accordance with these 2 values, PV1 and PV2. For the second setup, which is RL load, we will supply to the primary side once 140 volts, and we'll adjust secondaries power factor, and we will change R values. Like there will be 6 steps and 6 values of resistance having same amount of power factor on the load side. So we'll do that. So for that, let's go and see how we actually managed to conduct the experiment. Hello. So as already explained, today we're going to do efficiency test of single phase transformer. So this is the setup. So we are going to experiment in different steps. So initially, as a load of this transformer, we will have to use R, and then after that we'll have to use this L. So initially we'll deal with R load for different steps. Like we already know there are 6 steps to increase the value of resistance. So we will change each step and measure the value and take notes of those values, and after that we'll calculate what is the efficiency. So efficiency is nothing but output power over input power. So we're gonna supply from this AC power supply to the primary of this transformer. We'll supply fixed 140 volts, and we will see what's the input power and power factor and output power and output power factor for R load. For RL load, we will fixed
we'll make sure that the power factor of the secondary side, which is the close to the load side, it has to be 0.8. So that is a must we need to focus on. So let's start supplying to the primary. Oh, I forgot to mention another thing. So after supplying the primary 140 volt for, say for example, for our load, we will flip the supply to the secondary, and we'll supply to the secondary, and primary will be connected to the load. So same to these two steps will be repeated. We will repeat this step for RL load as well. So let's start then. So let's turn this on, make sure the input voltage is 0. So we'll increase the voltage up to 140 volts. Even if it is like a little bit more than that, it's also all right, but we want to be precise value. So since I haven't actually connected any of, like, switched on any of the low resistive loads, so the output power is near to 0, although we have voltage which is 70 voltage, so it is half of the voltage. So we know that we are in right track. So let's turn on switch 1 for the resistor. You will see there are some changes in power. So there are also, you will notice we have current. So we don't need much of the information for this experiment. We'll need only input power for each step. So I'd like you to actually take reading and like take notes of on these readings. Like the input power is 3.8, power factor is 0.87, and the output power, that means PV2, is 2.5, and power factor is 1. Now we'll change the resistance value. We'll step it up. Now we'll see that the input power is 6.3 and the power factor is 0.91, having the same input voltage. So the output power is 5 and power factor is 1. Then we will switch it up a little bit more. Then we'll see that input power is 8.6 and power factor is 0.96, and output power is 7.3 and power factor is 1. Because this is a resistive load, we're gonna increase it. So the input power is, for step number 4, the input power is 11 and power factor is 0.961, whereas output power is 9.7 and power factor is 1. We'll do the same. This is now step number 5, 13.4, power factor is 0.969, and here the output power is 12 and power factor is 1. And the next one will be the last one for this case. So input power is 15.6 and power factor is 0.976. Output power is 14.2 and power factor is 1. So that's all for case 1. Now we will turn this to 0 voltage and turn this off. Then we will switch the power supply from primary to secondary. So we'll open these two and we'll connect the load to the secondary and primary, and supply from the secondary. So the supply voltage will directly go and energize the transformer from secondary, and secondary, and the primary is connected to the load via this power analyzer. So, and we will repeat the whole thing again. So I'm turning the switch on, dialing the voltage to 70. Why it is 70? Because now we are supplying to the, what is it called, secondary side, and we know this is the low voltage side and this is the high voltage side. If we supply to the high voltage side with 140 volts, so we'll get on the secondary 70 volts, and if we supply 70 volts here, we'll get 140 volt on the primary or high voltage side. So that's why we're gonna supply 70 volts here, not more than 70 volts. Let's see, I forgot to switch on the resistors, switch off the resistors, sorry. Yeah, that's about it. So 70 volts to the primary secondary side, and on the primary side we get like 140. Okay, let me adjust, it's supposed to be 140. Yeah, exactly like the second one, previous one. So it is 69.8. So it'll be, let me adjust a little bit more. Yeah, that's about it. So now we will switch on the first step. We'll measure the power. So power is the supply power is 11.4. 0.9 is the power factor, that is the power supply, and output power, input power was that previous one, and this is the output power, which is 8.3, and power factor is 0.958. Let me switch on the second one. You will see the input power is 20.7, power factor is 0.979, output power is 17.4, and power factor is 0.97. So we will turn on the third one, 29.5, and power factor is 984. This is the output power is 25.7, and power factor is 0.98 or 0.99. We'll turn on the fourth one. The input power is 37.9, and power factor is 0.99. The power for the secondary is 33.4, and power factor is 0.99. We'll switch it on. We switched on the fifth one. Input power is 46.7, power factor is 0.99, and here is the secondary side. That means 41.2 is the output power, and power factor is 0.993. Let's turn on the final one, which is sixth. So input power is 54.8, power factor is 0.992, and output power is 48.5, and power factor is 0.997. So power output power means PV2 for this case, and input power is PV1 for this case. Although we are supplying to the secondary, it doesn't really matter. If we supply to the secondary, then it will become V1 and this will become V2. So if we supply this, then it will become again it will become V1 and it will become V2. So it works this way. Now we are gonna switch everything off. Like now we will connect this load, this L load, with parallel to this R load. So, and we'll have to adjust the power factor. For this case, the power factor has to be 0.8 for all the steps. So we'll have to dial it, sometimes dial it up, sometimes dial it down according to the measurement what we are gonna get. Let's do this. Let's apply the, let me switch everything off. I'm turning it on, and since we are supplying the secondary voltage, secondary side, so this will the voltage has to be 70 volts. We're gonna disconnect everything and do everything for the primary side, but let's do the secondary side first. So let's do it. Okay, 70. So supply voltage is 70. Let's turn this on. Now let's look at the power factor and input power, output power. So these are the readings of output power and output power factor. As I told you that we need to actually change the power factor by changing the value of inductance, so that the power factor becomes 0.8. So we'll have to make it, yeah, that's about it. So yeah, 0.8. So now for step number 1, the input power is 16.1, power factor is 0.817, output power 12.7, and power factor is 0.8. Now we'll switch the second one on. Now if we look at the power factor, it becomes 0.9, so we'll have to dial it down. Okay, that's about it. So for second step, the input power is 25.7, power factor is 0.821, and output power is 21.8 or 7, power factor is 0.8. So why is every time we increase the value of resistance, the power factor goes up? Because we know if a circuit has too much inductance, then we'll have power factor, a very bad power factor. Say for example, if the inductance value is 50% more, then power factor will be like 0.5. Say for example, if we increase the amount of inductance from that point, the power factor will go down. So but if we increase the amount of resistance, that means in the circuit overall the resistance, the value of resistance is higher. So if the value of resistance is higher compared to the inductor, then we'll get a power factor, we'll get better power factor. So that's the case. But in reality what happens is, to minimize the amount of inductance, we include leading power factor components, say for example capacitance, because we the loads are fixed normally, right? We cannot use too much load. That is another way to do it, but that is not a right way to do it. Otherwise we'll have to put bills, like more bills, because the loads are equipments, right? So if you put too much equipment, unnecessary equipment, if you don't need it, but if you still use those equipments or resistive loads, that means you will have to pay more bill. So the smart way to do is use capacitance across the loads, so that we call it power factor correction panel. So it's normally connected in the utility section of any house or any residential loads, or if the load is too much, in that case residential load, normally we don't put it in residential loads. In some cases we do, but in most cases in industrial loads we use capacitor banks as power factor correction panel near the utility section. Anyway, so for a second step, I have already gave you guys the input power 25.6, power factor is 0.82 for the primary side, so for the input side, and the output side is 21.7 and power factor is 0.8. We'll switch it on the third one, then we will see the power factor went up again. We'll have to reduce the amount by increasing the inductance. Okay, so that's 0.8. so the input power for step number 3 is 34.9 and power factor is 8.82. The output power is 30 and power factor is 0.8. We'll go from 3 to 4 now, so and we'll have to adjust power factor. Yes, so for this case input power is 44, power factor is 0.82, output power is 37.8 or 9, power factor is 0.8. We go from 4 to 5 and adjust power factor. Okay, so for step number 5, the input power is 52.8, power factor is 0.82, output power is 45.2, power factor is 0.8. Now this is the last step. We'll have to increase yet again the value of inductance. Okay, for step number 6, the input power is 61.7, power factor is 0.8. For output section 52.2 watt and power factor is 0.8. Now we're gonna switch everything off. We'll step it down. Now the supply voltage should also be 0, and we will change the connection. We supply it to the primary side, this one high voltage side, and the secondary side, in this case X1 to X7, is connected to the RL load. Now switch the power. The last step, the power supply is 140 volts. Okay, supply is 140 volt. We'll switch the first step on. Power factor needs to be 0.8 for each case. So this is power factor 1 for case 1, power factor. Okay, I need to change again. It's a very tricky part. That's about it. So for first step, the input power is 5.2, power factor is 0.71, output power is 3.9, power factor is 0.8. Step number 2, we need to adjust power factor again. Once again, it's a tedious work, but it is what it is. We'll have to manage it. So let's say this is 0.8. So in for step number 2, input power is 7.7, power factor is 0.731, output power is 6.4, power factor is 0.8. Step number 3, we'll have to adjust once again the power factor for each step. Okay, for step number 3, input power is 10.2, power factor is 0.75, and at the output side, output power is 8.8, power factor is 0.8. Step number 4, we are adjusting the power factor. Okay, so for step number 4, input power is 12.8, power factor is 0.76, and output power is 11.2, power factor is 8.8. Step number 5, again we need to adjust power factor. Okay, for step number 5, input power is 15.3, power factor is 0.775, output power is 13.7, power factor is 0.8. Now we are gonna go to the last step, which is step number 6. We need to adjust power factor once again. So unfortunately we cannot increase the amount of power factor, so we reached the last point, so we cannot actually improve the power factor, increase the amount of inductance anymore. So this is the maximum amount of power factor reduction we can do, so we'll have to use this one. So for step number 6, input power is 17.7, power factor is 0.79, and output sections 16 watt is the output power, and power factor is 0.829. So with all those information, so measurements value, you need to actually make table like this. There will be 4 tables. Table 1 will have will be for R load, and when we supplied to the primary section, and table 2 will be for 70 volts when we supplied to the secondary side, and table 3 will be for R load having when we supply to the primary side, and finally table 4 will have RL load, will be for RL load, and when we supplied to the secondary. So if we actually make a table like this, there will be 4 tables, so we'll have to put values here, like all the reading values, and finally we need to calculate the efficiency. And to calculate the efficiency, we need to use this formula, the first one, which is this one, and after that we need to draw a waveform like this, where x-axis will have PV1 and y-axis will have PV2. So there will be 4 waveform for 4 of these tables. So you'll have to use each step values, like say for example, initially when we switched on number 1 resistor, we got 2 values. One is PV1 and PV2, so we need to plot these 6 steps here in the what is it called, waveform, and we'll get 4 waveform, and we will actually compare each table or compare the graphs, and we'll analyze everything. So in theory lecture,
So yeah, that's about it. So we're gonna do that, and let's go to this report section. So this is the manual. So um, for experiment number 5 and 6, you need to actually put calculation steps and schematic diagram, schematic diagram. There will be two circuits because we use two circuit, like one for resistive load, one for RL load. So we're gonna draw two schematic diagram, and there will be 4 tables. You need to include those tables, and calculation for each steps on that table should also be there, and comparison between different tables, like say for example comparison between table 1 and 2, 3 and 4, and then comparison between R load and RL load. So you need to compare those table data, as well as you need to plot uh, what is it called? Plot four waveform, uh, from those datas, table datas. So that's all for today. If you have any question, you can ask. Uh, that's it. Thank you. Have a nice weekend.